All right, let's finish off section K.3. In this video, we're talking about the ratio test, and then I'll give you a little bit of bonus math, as I promised, with the root test. Let's look at them both right here. The ratio test up top. This can be used for both positive series as well as alternating series. It's going to be really useful for us when we see factorial. So that's kind of your clue that you should probably be trying the ratio test. What we're going to do is we're going to look at the ratio of the absolute value of the n plus 1th term to the nth term. We're going to calculate the limit as n approaches infinity. One of three things is going to happen. We're either going to get a value, assuming that the limit exists, we're going to get a value that's less than 1, greater than 1, or equal to 1. Hopefully we're getting one of these two. If the value is less than 1, then our series, our original series, converges. Not only that, it converges absolutely. And if our limit ends up being greater than 1, okay, then our original series diverges. Trouble happens when we get the limit being equal to 1. The test is inconclusive. We don't know whether the series converges or diverges. We'd have to try something else. And we can just look at the root test down below. In that, we're going to take the absolute value of the nth term of the sequence and take the nth root of it. And we can see kind of the same behaviors happening over here. If we get a value less than 1, then our original series converges absolutely. Greater than 1, it diverges. Equal to 1, it's inconclusive. So these tests are often presented together. But the IB does not require the root test. But I mean, I don't know. Like, let's just do it. It's so similar to the ratio test. Why not? If you're self-studying for BC calculus, the root test is something you need to know there anyway. So I think it's worth taking a peek at. Oh, your clue for the root test will be that you'll have some expression that has n as both a base and as an exponent. We'll see an example of that in a few minutes. There'll be n's in some like large expression, and then it will also be raised to the power of n. And that's kind of leading us towards taking the nth root of it. But anyway, let's start with the ratio test. Okay, here's a positive series. We're going to prove that it converges. Incidentally, if it didn't say prove that it converges, my first step, always try the nth term test. It's not really obvious here what the limit is here as n approaches infinity. 2 to the n and n factorial are both growing, but it's not obvious which one grows faster. We can't use L'Hopital's rule on that because I don't know what the derivative of n factorial is. So what we're going to do is the ratio test. Right, so absolute value of the n plus 1th term divided by the nth term. We're always going to write this as a product, so we're going to take that nth term, flip it over, and write it as multiplication. Personally, I'm not writing this step here. I'm just looking at what I've got going on right here. I see that the n factorial and the n plus 1 factorial, they're going to cancel out, leaving behind just an n plus 1. I see the 2 to the n plus 1 is going to cancel out with 2 to the n, leaving just a 2. And that's the beauty of the ratio test. We're always going to have a whole bunch of stuff canceling out. So what's the limit now? As n approaches infinity, here, the limit there is clearly going to be 0. So we've got a value that's less than 1. Therefore, our series converges by the ratio test. Awesome. Let's do one where it diverges. I guess I just spoiled the answer for you, but we're going to do the same thing here. Again, I'm noticing the n plus 1 is going to cancel with the n factorial. The 1,000 to the n plus 1 is going to cancel with the 1,000 to the n. The limit now, we're getting infinity, diverges by the ratio test. So you notice in the last two examples, the factorial grew faster than the constant raised to the power of n. Turns out that's always going to be true, no matter what that constant is. And I usually stay away from bothering with the proofs in these videos, but the proof for this one is super brief and super easy to see just by using the ratio test. So that's always going to be the case. I would not rely upon this. I mean, if you see a series of the form, 5 to the n or whatever over n factorial, uh, don't just tell me that it converges, because obviously don't tell me that it converges for this fact. Don't cite that. Please use the ratio test to gain full credit for the IB. Finally, let's just look at two trivial examples just to see how the ratio test can be inconclusive. So on the left, we've got the series n squared, which obviously diverges. It doesn't pass the nth term test. And on the right, we've got n to the negative 2. That's 1 over n squared. That's going to converge. That's p series. P equals 2. We're good to go. But in both cases, as you can see, the limit as n approaches infinity of the ratio is equal to 1. So that's why we can't really be sure what's going to happen there. We'd have to check some other test. Now, obviously, if these were the series, I wouldn't use the ratio test. It's much easier to think of in other ways, but just illustrating the point that we can't be sure. Finally, let's just look at one root test just so you can kind of see how this thing operates. So we can see, I mean, this one's crazy looking. It's not geometric, even though we've got the exponent of n up there. I don't know what's happening as n approaches infinity. We've got infinity over infinity to the infinity. That could be anything. So we use the root test. The root test, recall, means we're going to take the nth root of the sequence. Taking the nth root of the sequence just means we're not going to use that part. So we're just going to check what's the limit as n approaches infinity of the remaining piece. That's 1/2. That's less than 1. Series converges by the root test. The IB wouldn't ask you one that requires the root test, but it's easy. I don't know, maybe there's another way to approach this one, but why would you do it any other way? Anyway, K.3, done. That means our series convergence tests are done. This is a great time to go to the class site and download the sequences and series big idea document to take it all in one last time. Read through all the different tests that we have. At the end, I've got my own kind of order that I like to go through them, depending on what I see. Although our textbook does not include something like this, most good calculus textbooks will include a section at the end of their series convergence chapter that'll kind of walk you through the process. You can also just look online. There's plenty of examples of like flow charts as well as written out sentences that'll kind of help you make your way through these. But beyond that, what do you need to do? I've said it before, we need to practice as many series problems as we can. When you get stuck, hop on over to Symbolab, just type in your series, and it'll tell you what test it thinks you should use, which in my experience is generally the easiest one, although it's not always the only one. Okay, so we've got to practice, practice, and practice some more, and eventually it becomes easier. You start to see the patterns in the series. You start to anticipate which test you should use first, so you're not wasting your time trying to figure out, like which one of those 10 things should I try. All right, that's the end of this video. That's the end of K.3. K.4 is going to really start to bridge the gap into section L. Section L is about Taylor and Maclaurin series, which are very specific types of something called a power series, and that's what we're going to see in the next section.